Our bodies are constantly communicating. They're sending out these incredibly intricate signals, even images that whisper secrets about our health, sometimes way before we feel anything's wrong. Today, on the deep dive, we're trying to cut through all that noise, understand this kind of invisible language of the body. We're doing a deep dive into biomedical signal and image processing, and we're drawing our insights mainly from the really comprehensive book by Kavan, Nagarian, and Robert Splinter. Our mission today, it's really to unpack how we capture, process, and interpret these biological messages, how we turn this complex data into insights that are vital for diagnosis and maybe even personalized health down the line. Think of it as your shortcut to understanding what your body is actually trying to tell you. So let's start with the absolute basics. When we talk about a signal in this context, what are we really talking about?
Right. Well, at its core, a signal is just a way to represent some physical phenomenon, something changing, like a voltage fluctuating over time. Now, if we measure something that's continuous, like a smooth wave, that's an analog signal. But computers need things discrete, so we convert them. We sample that analog signal at specific points in time, making it a discrete signal. And then if both the time and the amplitude, the signal's strength, are defined at discrete points, that's what we call a digital signal. And interestingly, most biomedical signals we actually measure, your heart's rhythm, brain activity, they end up being discrete or digital because that's just how our instruments capture them.
Okay, so we've got these raw signals. They're packed with information, I assume, but probably also like interference, noise. How do we make them useful? How do we get clear insights?
Yeah, that's exactly where the processing comes in. It's absolutely crucial. There are really two main steps here. First, we filter the signal. Imagine trying to listen to one specific radio station, right? But they're static, maybe another station bleeding in. Filtering is like tuning that out. So for an ECG, your breathing creates electrical signals that can kind of interfere with the heart signal. We filter those out to see the heart clearly.
It makes sense, like noise cancellation.
Precisely.
Yeah.
Then the second step is feature extraction. This is where we identify specific telling characteristics within that cleaned up signal. Things like, how high a peak is, how wide a wave is, how often something repeats. These extracted features, these are the things that help doctors distinguish between, say, a healthy heart rhythm and an abnormal one. They're the body's telltale signs.
And to really dig into those features, I know we use some pretty heavy-duty mathematical tools, the Fourier Transform, for instance.
Absolutely. The Fourier Transform, or FT, is a real cornerstone. It's this amazing tool that lets us shift our perspective. We move from the time domain,
where you see things happening over time.
Exactly, like tracking the exact moment you go shopping.
Yep.
The FT lets us move to the frequency domain. So instead of asking when you shop, we ask, how often do you go shopping? Or maybe, what percentage of your shopping happens on weekends?
Okay. Different questions from the same data.
Right. And the power here for biomedical signals is it lets us dissect these complex biological signals into their fundamental frequencies, their underlying rhythms. It can reveal hidden patterns or anomalies that might be completely buried if you just look at the signal changing over time. It's like finding a specific melody hidden within what just sounds like noise.
That sounds incredibly powerful. The source also mentions something specific, that an impulse function's frequency spectrum is completely flat. What's the significance of that?
Yeah, that's a really interesting property. An impulse, a super brief, sharp spike, it's so sudden it essentially contains all possible frequencies at equal strength, like a burst of white noise, in a way. Also, crucially with the Fourier transform, if you just shift a signal in time, it happens a bit earlier or later, it doesn't actually change the magnitude of its frequency component.
Okay.
It only changes its phase. Think of it like a ripple in a pond starting a fraction of a second later. The ripple itself, its size and frequency, is the same.
I see. So the pattern is still recognizable, even if the timing is slightly off.
Exactly. And that resilience is incredibly useful when you're dealing with biological data, which can be noisy or sometimes captured irregularly. We can still pull out the underlying biological pattern.
You mentioned the FT simplifying calculations. There's another term that comes up a lot, convolution. How does the FT help there?
Right, convolution. It's a fundamental operation, especially in linear systems. It basically describes how one signal or pattern modifies another, or how an input signal gets transformed by a system to produce an output.
But are biological systems really linear? I thought they were more complex.
That's a great point. And you're right, most biological systems are inherently nonlinear. They don't always respond predictably, which is part of what makes them so adaptive and interesting. But even so, the Fourier transform provides a way to simplify the mathematics of convolution significantly. It turns convolution in the time domain into simple multiplication in the frequency domain.
Okay. Much easier.
Much easier. So even for these complex nonlinear systems, the FT gives us a powerful way to approximate and analyze their behavior, extract meaningful insights. And what's fascinating here is how these transforms, like the Fourier and the wavelet transform, allow us to sort of listen to different aspects of the body's signals. They reveal details that just aren't obvious if you only look at a time plot. The wavelet transform, especially a discrete wavelet transform, or DWT, kind of takes this a step further.
How so?
Well, unlike the FT, which looks at frequencies across the entire signal duration, DWT can analyze different frequencies at different points in time. It gives you a more localized picture, like zooming in on frequency content in specific moments. It can handle continuous signals, but it applies discrete shifts and scales using these specialized mathematical functions called mother wavelets.
Mother wavelets, like Debye's Har?
Exactly. Things like Debye's Har, Queuflets, and the choice of which mother wavelet to use really depends on the signal you're looking at. For something like an ECG, maybe a simpler one like dB10 or dB15 is enough. But for really complex signals, like speech, you'd need a more intricate wavelet to capture all the nuances.
So how does this translate into something practical for, say, someone listening? How does DWT help in the real world, maybe with brain activity?
Oh, absolutely. Denoising is a huge application. The DWT is excellent for cleaning up signals. Imagine you have an EEG signal, but it's corrupted by high-frequency noise, maybe from tiny muscle movements near the scalp or electrical interference.
Right, happens all the time.
So you can use DWT to decompose the signal into different frequency layers. You identify and remove those high-frequency components that are just noise. Then you reconstruct the signal using only the lower frequency physiologically relevant parts. And this can reveal crucial information. For example, in an EEG, a really strong low-frequency component could indicate that the patient is asleep or maybe drifting off. That's vital physiological information that might be completely hidden by noise without this kind of wavelet processing.
Wow, okay. It's like fine-tuning the signal to hear the important message.
Exactly. It lets you hear the clear voice through the static.
So let's connect these concepts to something really tangible, the heart. How does all this signal processing actually help doctors understand what's happening inside your heart? Let's talk ECGs.
The ECG, the electrocardiogram, yeah. It's essentially a recording of your heart's electrical symphony. It captures the tiny electrical currents generated as the heart muscle cells depolarize and repolarize to coordinate the heartbeat. Processing these signals is key because it lets doctors spot abnormalities really early on, sometimes even before a patient has any symptoms. We can identify common arrhythmias like atrial fibrillation, AF, that's where the upper chambers beat chaotically, or more dangerous ones like ventricular tachycardia, VT, or ventricular fibrillation, VF, which originate in the lower chambers. Spotting these early can genuinely be life-saving.
Okay, so for something like VT, ventricular tachycardia, what specifically would processing reveal on that ECG? And what about other conditions? Are there unique signatures?
Yeah, VT has a pretty clear signature. It's characterized by a very fast heart rate, often over 120 beats per minute, and this results in rapid, wide QRS complexes.
The main spikes on the readout.
That's right, the spikes representing the main pumping action of the ventricles. That very high frequency is really easy to pick up in the Fourier domain analysis. Other conditions also leave fingerprints, right? Bundle branch block, RBBB, or there's a delay in the electrical signal in one part of the heart, shows up as a QRS complex that's wider than normal, typically over 0.1 or 0.12 seconds. And something like Wolff-Parkinson-White syndrome, WPW, which involves an extra electrical pathway, often shows a characteristic delta wave, a little slur on the upstroke of that QRS complex. Generally, for a normal ECG, we analyze frequencies from about 0 up to 100 hertz. But for arrhythmias, especially fast ones, we might need to look up to 200 hertz because important information about those rapid rhythms can be hiding in those higher frequencies. Anything higher than that is usually just noise.
Fascinating. Okay, let's shift from the heart to the brain. The electroencephalogram, EEG. What's involved in recording brain activity, and what can it tell us beyond just finding problems?
The EEG records the incredibly subtle electrical activity generated by brain cells communicating. To get a good picture, we use multiple electrodes placed on the scalp, anywhere from 21 standard ones up to 256 in some research settings. The amplifiers need to capture a wide frequency range, typically 0.1 to 100 hertz, to get all the details. EEG is invaluable for diagnosing things like seizure disorders, brain tumors, head injuries, even determining brain death. But beyond diagnostics, it's really a window into brain function. It gives us this real-time glimpse of the brain's orchestra, thought, consciousness, relaxation.
I've heard about different brainwaves, alpha, beta, delta. What do those actually represent?
Those are the main frequency bands we see in EEG activity, and each tends to correlate with different states. Alpha waves around 8 to 14 hertz are strong when you're awake but relaxed, maybe with your eyes closed, chilling out. Beta waves, faster, 14 to 50 hertz, show up when you're alert, actively thinking, concentrating, solving problems.
Okay.
Delta waves are the slowest, 0.1 to 4 hertz. They dominate during deep, dreamless sleep, but they can also indicate significant brain injury if they appear when someone should be awake. And theta waves, 4 to 8 hertz, are linked to drowsiness, light sleep, sometimes deep meditation or creativity. Beyond just these ongoing waves, EEG is used to study specific brain responses, evoked potentials, EPs, or event-related potentials, ERPs.
How does that work?
We present a specific stimulus, a sound, a flash of light, a word, and measure the brain's precise electrical response to it. This helps researchers investigate things like processing speed or latency, how quickly the brain reacts and processes that specific event.
I'm thinking about specific disorders. How does EEG help with diagnosing epilepsy or maybe finding brain tumors?
For epilepsy, EEG is absolutely critical. It helps confirm a diagnosis and classify the type of seizure. Is it general, involving the whole brain, like an absent seizure or a tonic-clonic one? Or is it partial, starting in one specific area? With brain tumors, EEG can sometimes reveal a focal source. Imagine looking at the electrical map across the scalp. You might see a localized area of abnormal slow-wave activity or sometimes sharp waves. This intermittent dipole indicates a disturbance, often greatest near the tumor's location, helping to pinpoint it.
Got it. Okay, one more signal before we move to images. EMG, electromyogram, for muscle activity. How does that work? How does a muscle even contract electrically?
Muscle contraction is amazing. It boils down to these tiny protein filaments, actin and myosin, sliding past each other. This is triggered by electrical signals from nerves. The muscle cells depolarize their electrical charge, changes they contract, and then they repolarize, resetting. This whole process involves flows of ions, like calcium. EMG measures the electrical potentials generated by these muscle cells during contraction and relaxation. It gives us direct insight into the health of the muscles themselves and also the nerves that control them.
So what kinds of conditions can EMG help identify? Issues with nerves or muscles?
Exactly. It can help diagnose problems like abnormal innervation, meaning the nerve supply to a muscle is damaged or destroyed, like what happens in polio. The muscle isn't getting the right commands. It's also key for issues with neuromuscular transmission, the communication point between the nerve and muscle. Conditions like myasthenia gravis, where that communication is blocked, leading to weakness. And disorders affecting motor control originating in the brain, like cerebral palsy, can also show up as abnormal patterns in EMG activity. Even something common like muscle fatigue has a distinct EMG signature. As a muscle gets tired, the frequency content of the EMG signal shifts. There's less power in the higher frequencies and more in the lower frequencies. We can measure this shift, often using high-pass filters, to get a quantitative look at muscle endurance.
Okay, so we've really dug into the signals, the ways we listen to the body. But sometimes listening isn't enough, right? We need to actually see what's going on. That brings us to biomedical imaging, literally painting a picture of our insides. Let's start with computed tomography, CT scans. How do they let us peer inside without surgery?
CT is really clever. It kind of works on this black box idea. We want to know what's inside the box of your body without opening it. CT does this using X-rays, but in a much more sophisticated way than a standard X-ray. It takes multiple X-ray projections from different angles all around the body section being scanned. The core principle is attenuation tomography, measuring how much the X-rays are weakened or absorbed as they pass through different tissues. And then complex computer algorithms, often involving principles related to the Fourier Transform, like the Fourier slice theorem, reconstruct these projections into detailed cross-sectional images, or slices. You can stack these slices to create 3D views.
So doctors can literally see inside. What are the big applications?
Oh, huge. Diagnosing strokes, injuries, cancers, and it's crucial for guiding procedures, like stereotactic surgeries for brain tumors, where surgeons need incredibly precise maps, or other image-guided interventions.
And how does a standard X-ray fit in? That's simpler, right? More like casting shadows.
Yeah. Exactly. Standard X-ray imaging is fundamentally about shadows and density. You pass X-rays through the body onto a detector, used to be film, now usually digital detectors. Different tissues absorb X-rays differently based on their density and composition. This is their attenuation coefficient. Bone is dense, absorbs a lot of X-rays, so it appears white or bright on the image. Soft tissues, air, they let more X-rays pass through, appearing darker. It gives you that classic view of bones, or maybe dense masses like some tumors or foreign objects. quick, effective for certain things.
Okay, now MRI, magnetic resonance imaging. This one always feels a bit like science fiction. What's the secret? How does it work with protons?
MRI really was a game changer. It's not science fiction, but it is incredibly sophisticated physics. The magic comes from the water in your body. You're mostly water, right? Which means lots and lots of hydrogen protons. First, a powerful magnetic field aligns these protons, kind of like tiny compass needles, all pointing the same way. Then the machine sends in brief pulses of radio frequency, RF energy. This knocks the aligned protons slightly out of alignment, causing them to wobble or precess. When the RF pulse stops, the protons relax back into alignment with the main magnetic field. As they relax, they release subtle energy signals, which are detected by the scanner. The key is that protons in different types of tissue relax at different rates. We measure two main relaxation times, T1, spin lattice relaxation, and T2, spin-spin relaxation. These differing relaxation times create contrast, allowing the MRI to build up incredibly detailed images distinguishing between gray matter, white matter, fluid, fat, muscle. It's listening to the magnetic echoes of your body's water. And it was pioneers like Raymond Domanian noticing that cancerous tissue had different relaxation times than healthy tissue, and Paul Lauterbur and Peter Mansfield figuring how to use gradients to create actual images that made this possible.
Wow. And you mentioned this raised the question, how can something like blood oxygen levels tell us what the brain is doing? That's fMRI, right?
Exactly. That's functional MRI or fMRI, and often specifically bold imaging, blood oxygenation level dependent contrast. It taps into a neat property. Oxygenated hemoglobin, blood carrying oxygen, and deoxygenated hemoglobin, blood after oxygen is used, have slightly different magnetic properties. When a brain area becomes active, it calls for more oxygenated blood. This changes the local ratio of oxy to deoxyhemoglobin. This tiny change subtly alters the magnetic field locally, and the fMRI scanner is sensitive enough to detect that change. So it's not directly imaging neural firing, but the blood flow response to neural firing. It lets us map brain activity.
So it's not just seeing the brain structure, but seeing it in action. What are some critical uses for fMRI then?
Oh, it's huge for research and increasingly clinical work. It helps diagnose conditions like epilepsy by pinpointing seizure origins, understanding schizophrenia, Alzheimer's, Parkinson's. Surgeons use it to map critical areas like speech or motor control before operating on a brain tumor to avoid damaging vital functions. It's used to study how the brain processes sound, investigates learning disabilities like dyslexia, maps motor activity, the list goes on. And often you'll see fMRI activation maps overlaid onto high-resolution anatomical MRI scans, or maybe even PET scans, to get both the functional, what's happening, and the anatomical where exactly.
Okay, let's switch gears to ultrasound. Using sound waves instead of X-rays or magnets, how do sound waves create pictures?
Ultrasound works by sending high-frequency sound waves into the body using a transducer probe. This probe typically uses special materials, often piezoelectric crystals, that vibrate when electricity is applied, creating sound waves, and conversely, generate electricity when returning sound waves hit them. The imaging relies on how these sound waves interact with different tissues. Two key properties matter: acoustic impedance, which is like a tissue's resistance to sound passing through, and the attenuation coefficient, how much it weakens the sound wave. When the sound wave hits a boundary between two tissues with different acoustic impedances, say between fat and muscle, or muscle and bone, some of the sound wave reflects back as an echo.
Like sonar.
Exactly like sonar. The probe detects these returning echoes. By measuring the time it takes for echoes to return and their intensity, the machine can build up an image of the internal structures. This is primarily reflection tomography. There's also attenuation tomography, looking at how much the sound weakened.
What are the main pros and cons of ultrasound compared to, say, MRI or CT?
Big advantages are cost and portability. Ultrasound machines are much cheaper and smaller than MRI or CT scanners, making them widely accessible, even bedside. Plus, it doesn't use ionizing radiation like X-rays or CT, so it's generally considered safer, especially for things like monitoring pregnancies.
But there must be downsides.
Definitely. Sound waves don't travel well through air or gas, so imaging structures behind the lungs or bowel can be difficult or impossible. Dense bone also blocks ultrasound waves, limiting views. And while generally safe, very high-intensity ultrasound can potentially cause tissue heating or mechanical effects like cavitation, forming tiny bubbles, though diagnostic levels are typically well below that threshold. Processing-wise, the source notes that wavelet analysis, especially Dobitsch's wavelets, often works really well for ultrasound images. Those sharp reflections from tissue boundaries are kind of like binary events, and that type of wavelet is good at representing those sharp changes, leading to clearer images.
Right. Okay, last major one, PE scans, positron emission tomography. You mentioned this is more about function than just anatomy.
Yes, that's the key differentiator for PT. Unlike CT, or standard MRI, which shows structure, PT shows functional chemical processes happening in tissues. It provides metabolic snapshots. And because disease often starts with functional changes at the cellular level, PT can sometimes detect abnormalities before they cause structural changes visible on other scans, even fMRI sometimes.
How does it actually work? Positrons, gamma rays?
It starts by injecting a small amount of a radioactive tracer into the bloodstream. These tracers are molecules, like glucose, tagged with unstable radioisotopes, things like carbon-11, fluorine-18, nitrogen-13, oxygen-15. These isotopes decay by emitting positrons, which are like anti-electrons. A positron travels a very short distance in the tissue before it bumps into an electron. When they meet, they annihilate each other, converting their mass into energy in the form of two gamma rays that fly off in exactly opposite directions, 180 degrees apart.
Okay.
The PET scanner is essentially a ring of detectors surrounding the patient. When two detectors on opposite sides of the ring detect gamma rays at the exact same instant, a coincidence event, the system knows the annihilation happened somewhere along the line connecting those two detectors. By collecting millions of these coincidence events, sophisticated algorithms can reconstruct an image showing where the radioactive tracer accumulated in the body.
And where the tracer accumulates tells you about metabolic activity.
Precisely. For example, using a glucose tracer, FDG, areas with high metabolic activity, like most cancer cells or active brain regions, will take up more glucose and thus show up as hot spots on the PTT scan.
So what are the primary uses? Cancer, heart, brain?
All of the above. PKI is huge in oncology for diagnosing many types of cancer: brain, breast, lung, lymphoma, melanoma, etc. Staging it, checking if treatment is working. In cardiology, it assesses heart muscle viability, blood flow. In neurology, it helps diagnose conditions like Alzheimer's by showing patterns of reduced glucose metabolism or Parkinson's or locating seizure foci. And just like with fMRI, PT images are almost always fused or registered with CT or MRI scans acquired at the same time. This PTT, or PT-MRI fusion, combines the functional PT information with the detailed anatomical map from CT or MRI, giving doctors the best of both worlds.
Incredible technology. Now, beyond these major players, the source briefly mentions a few other glimpses into the body, like microscopy.
Right. We shouldn't forget microscopy. From standard optical microscopes letting us see cells, to advanced confocal microscopy giving clearer 3D views of tissues, and then electron microscopy, TEM and SEM, which lets us see way smaller structures, like organelles inside cells, viruses, even connections between neurons. It's fundamental for understanding biology at the cellular level.
And thermographic imaging, seeing heat.
Yeah, the thermography is another functional method. It basically creates a heat map of the body surface. It can show areas of inflammation, which are often warmer due to increased blood flow, or areas with poor circulation, which might be cooler. It's not invasive and used in some specialized areas, like monitoring tissue temperature during certain treatments like laser therapies.
And finally, something many of us use daily without thinking about it as biomedical imaging. Biometrics.
Absolutely. Biometrics uses unique biological characteristics for identification. Imaging plays a key role. Fingerprints, for instance, analyzing the unique patterns of ridges, valleys, loops, whorls, and those delta-shaped formations. That's image processing. And retina scans, which map the unique topographical distribution of blood vessels on the back of your eye, the retina. The pattern is totally unique to you. Highly secure identification based on imaging internal biological structures.
Wow. We have covered an incredible amount of ground today, from those basic ideas of signals, the body's whispers, and the transforms we use to decode them, all the way to these amazing imaging methods like MRI, CT, ultrasound, PET that literally paint pictures of what's happening inside us.
It really is remarkable, isn't it, how technology lets us non-invasively see and listen to the body's intricate workings. These tools are truly the technological backbone of so much of modern medicine. They allow for earlier diagnosis, more precise treatments, a much deeper understanding of health and disease. They give doctors this incredibly clear, comprehensive view inside your body.
So hopefully you, listening, now have a clearer picture of this complex but vital field. You understand a bit more about that invisible language your own body is speaking all the time. And maybe here's a thought to take away. Consider how every one of these signals, every image, tells a unique story about your health right now. If we keep getting better at reading these stories, just imagine what new depths of human health, what diseases might we uncover next, maybe long before any symptoms even start to show.
Okay, that was Notebook LM, as you can hear. Let me know if there's any questions. Everything we do goes on to bionichaos.com. Go check it out. Let us know what you think. Chat. So there's a link to all the tools in the chat. Hey, go check them out. They all now have automations. They have an audio description. That's a different description from what you just heard. So you can adjust this one's. You can select your signal type. Also have sonification. Why sonification doesn't work? Yeah, chirps, ball strains. Yep. White noise. We have EEG signals. That's what they sound like. Yeah, there's an interesting thing with ECG. So I have normal sinus rhythm. Can increase the heart rate. Can change the QRS duration. It makes this interesting change in the frequency domain and also the sonification of it. Can add some noise to it, just so it looks and sounds more realistic. Yeah, it's funny, every time I it's fine. People say they don't like AI, but then as soon as I start talking, my views actually tend to drop. Interesting. Very interesting. Anyway, we'll move to the next tool review. It's also pulling out some stuff from the web literature, scientific literature.